Hi, I was looking at the comments section of a YouTube video on nonlinear ordinary differential equations, and I saw that someone had asked how to solve y double prime squared plus y prime squared equal to 1, which we've got written down here in equation 1. So we are now going to attempt this question and see if we can find a solution to it. So what we do is we write down y. We'll use black ink, I think. There we are. So what we do is we write down y double prime all squared, but we move the y prime squared term over to the right hand side of the equal sign. So what we now have is 1 minus y prime all squared. So we'll call that equation 2. Now, y prime means dy by dx, and we let that be equal to p. So I should say let y prime be equal to p, right? This means that the second derivative of y with respect to x, that's the same as y double prime, is equal to dp by dx. I'm just going to write the derivative of p with respect to x in that form, dp by dx. I'm not going to call it p prime or anything. So we've now got y prime is equal to p, and y double prime is equal to dp by dx. So if we go on to the next page, I'll write down that equation once again, that equation 1. So we've got y double prime squared, and that is equal to 1 minus y prime squared. And it's actually equation 2, isn't it? So we've rewritten down equation 2. So we're now going to substitute p for y prime and dp by dx for y double prime. So we've got dp by dx all squared on the left hand side, and that's equal to 1 minus p squared. So we've substituted the p for y prime and the dp by dx for y double prime, and we'll call that equation 3. Right? So now what we can do is square rooting both sides of equation 3, we get dp by dx equal to the square root of 1 minus p squared. Right, and we'll call that equation 4. Okay, so now we've got a simplified equation where we've only got the first derivative of something with respect to x, namely the first derivative of p with respect to x on the left hand side. This is a simplified differential equation because now we don't have a squared term on the left hand side, which is complex and you can't really do anything with that. So we've, as I said, we've now got this in a form where we can manipulate the equation much more easily. So if we go on to the next slide, we can separate the variables to get, well, I'll just write it down again. We've got dp over, let me just go back to the previous page. So we've got dp by dx equal to the square root of 1 minus p squared. So if we bring everything on the right hand side down into the denominator on the left-hand side and then multiply both sides by dx, we get dp over 1 minus p squared equal to dx. So that's what we get if we separate out the variables. Now, just let's put the dividing line in there. Now, let me just see where we got up to. So we'll call this equation 5. Right, how do we solve this? Because it still looks complicated. Well, if you've done high school mathematics, what you will recognize is that if you let p be equal to sine of v, then dp is equal to the cosine of v dv, right? So equation 5 above becomes cos v dv all divided by 1 minus sine squared v. And we've got the integral signs there, and everything there on the left-hand side is equal to the integral of dx on the right-hand side, and we'll call that equation 6. Okay, so you might recognize that 1 minus sine squared v is actually an identity. In other words, it's identically equal to something else. So let's go on to the next slide. We know that cos squared v plus sine squared v is equal to 1. Therefore, cos squared v is equal to 1 minus sine squared v. And if you look at that, you've got 1 minus sine squared v. So what you replace that 1 minus sine squared v by cos squared v under the square root sign, so that what you get is, I have to go back to remind myself, is the integral of cos v dv all divided by the square root of cos squared v, and that's equal to dx. It's looking a little bit untidy on the left-hand side, but hopefully it's reasonably legible and you can see what I've written. So what's the square root of the square of the cosine function? Well, that simply becomes, we've got the cos v dv in the numerator of the fraction, and the square root of cosine squared v simply becomes cosine of v, and then that's equal to dx on the right hand side. Now let's just label these equations. So we've got 6, 7 there in case we need it, 8, 9 and 10. So you can see that in equation 10 we can cancel the cosine v straight away. So that if we go to the next slide, what we've got is, let's change back to black. So we've got the integral of dv is equal to the integral of dx. So this integrates really easily to give v equals x plus c1, right? But we know that p equals sine v here, right? We know that p equals sine v. So therefore v is the arc sine of p. So let's just write that down. I'll write this in red. Since And I've forgotten exactly what I've written down. So P, since P equals sine V, then V equals the arc sine or the inverse sine of P. Probably better to say inverse sine. That's what everybody generally uses now, but arc sine's okay. Arc sine and inverse sine mean the same thing. So therefore, we better label the above equation. So we'll call that equation 11. So therefore, equation 11 becomes inverse sine of P equal to x plus C1. Right? So we've just replaced V with inverse sine P, and that's equal to x plus C1. Now, if we go on to the next slide, we can take the sine of both sides, and that becomes P equals sine of x plus C1, right? But we're still not quite finished, because if we go right back to the beginning, you can see that P is equal to dy by dx. P is equal to dy by dx. So if we go back here, we've got, we'll just write it out, but P equals dy by dx. So, and we better label that equation. We'll call that equation 12. And so this is equation 13. So equation 13 becomes d. Well, let's change back to black. So we get dp. I beg your pardon. We get dy by dx is equal to sine of x plus c1. Right, we'll call that equation 14. So we've simply replaced the p with dy by dx. So dy by dx is now equal to the sine of x plus c1. This is really easy to integrate, because all you do is separate out the variables and put in the integral sign. So you get the integral of dy on the left equal to the integral of sine of x plus c1 dx on the right hand side. I'm going to call that equation 15. So integrating, we simply get y equals, well, first of all, we've got a constant of integration, so we'll call it constant 2, C2, and that's equal to minus cosine of x plus C1. And that is the solution to the original differential equation. Y equals C2 minus the cosine of x plus C1. And we'll just label that as equation 16. My writing isn't always very clear. Many apologies for that. We'll just make that look more like an X. My X's don't always look like X's. Once again, many apologies for that. Well, that basically brings us to the end of the video. I hope you've enjoyed that, and that you will come back and see more of my videos in the future. So I'll bid you farewell for now, and I'll say goodbye.